Previously, we determined the empirical formula for an ionic compound where the empirical formula and chemical formula are the same. In this video, we do the same for a molecular compound where the empirical formula and the molecular formula are not necessarily the same. A typical problem we might come across for molecular compounds in determining empirical formulas and chemical formulas is this one here. 8.60 grams of a hydrocarbon sample contains 7.11 grams of carbon and 1.49 grams of hydrogen, and we're being asked to determine the empirical formula and then the chemical formula using the additional information that the molecular mass of the compound is 58.12 atomic mass units. The way we're going to tackle this problem is to determine the empirical formula first, and then we will use the molecular mass data to work out the actual chemical formula. We can write down the empirical formula of any hydrocarbon as CXHY, where the subscripts X and Y are the whole number subscripts in the empirical formula, and they represent the mole ratio of carbon and hydrogen in this as yet unknown compound. And I should just point out that for hydrocarbons, that is compounds containing just hydrogen and carbon, the carbon is always written first and the hydrogen is written last, which goes against the general rule of writing the most electropositive element first and the most electronegative element last. And we will note many times throughout this video series that hydrogen is often an exception for many general rules. This particular problem gives us the actual mass values of each element in grams, unlike previously where we had mass percentage data. So our 8.60 gram hydrocarbon sample contains 7.11 grams of carbon and 1.49 grams of hydrogen, which means that we can use our molar mass equation to directly work out the moles of carbon and the moles of hydrogen in this 8.60 gram sample. Setting aside the general molar mass equation of moles equals mass divided by molar mass, we can calculate the moles of carbon first by dividing the mass of 7.11 grams by the molar mass of carbon, which is 12.01 grams per mole. And remember, we just get that value directly from the periodic table. So the moles of carbon end up being 0.592 moles of carbon in our 8.60 gram sample. We do the same for hydrogen. Moles of hydrogen equals the mass of hydrogen, being 1.49 grams, divided by the molar mass of hydrogen, which we get from the periodic table as 1.008 grams per mole, rounded to 4 significant figures. Plugging those numbers into our calculator, we get 1.48 moles of hydrogen in the 8.60 gram sample. So the 0.592 moles of carbon is essentially related to the subscript for carbon, and the 1.48 moles of hydrogen is related to the subscript for hydrogen. And we could write down the empirical formula like this by substituting these values in, but we know that empirical formulas need to have whole number subscripts. So the easiest way of getting these numbers into whole numbers is to identify the smaller of the two mole values, being 0.592, and we divide each of the mole values by this value. So 0.592 divided by 0.592 and 1.48 divided by 0.592 gives us values of 1 and 2.5 respectively, which represents the mole ratio of carbon to hydrogen as 1 to 2.5. But we still don't have both numbers as whole integer values, which is required for empirical formulas and for chemical formulas. The simplest way to make this a whole number ratio is just to multiply both of those subscripts by 2 so that we get C2H5 being the empirical formula for this compound. It's also worth pointing out that this is the empirical formula for a molecular compound and that the molecule C2H5 does not actually exist. Rather, C2H5 is the lowest whole number ratio of carbon and hydrogen in a compound, and that the actual molecular formula will be a whole number multiple of the subscripts in the empirical formula. So we can write down the empirical formula on the left-hand side as C2H5, and we can use some new subscripts for the actual chemical formula, CaHB. And we can ask, what are the actual values of A and B? Well, they are going to be whole number multiples of 2 and 5. And how do we determine exactly what they are? Well, we know that the molecular mass of the actual compound is 58.12 atomic mass units. Now, if we were to look at the molecular mass for the empirical formula, C2H5, we calculate that 2 times the atomic mass for carbon plus 5 times the atomic mass for hydrogen is 29.06 atomic mass units. And the ratio between these two values is equal to 2. So when we're trying to determine the actual chemical formula of this compound, we're going to take the subscripts in the empirical formula, and in this case, we're going to multiply them by 2. So what we end up with here is the compound C4H10, and this is the chemical formula for the compound referred to in the question above. To summarize, if we are given the mass of each element of a compound in a sample and asked to determine the empirical formula and chemical formula, we start by calculating the moles of each element using the molar mass equation. We then determine the mole ratio of each element by dividing the moles of each element by the lowest calculated value of moles for all the elements involved. And that mole ratio gives us the empirical formula. Lastly, we know that the subscripts in a chemical formula will be a whole number multiple of the subscripts in the empirical formula, and we will use the molecular mass or molar mass data to work out what the chemical formula will be.